Hello everyone, this is the presentation of research titled Encoder-Decoder based convolutional neural networks with multi-scale aware models for tackling crowd counting. I am Pongpisit Tanasutuet from Osaka University. Crowd counting is a task where the goal here is to count a number of people in a given image for public safety, surveillance monitoring, etc. But there can be some problems along the way. First, you can have heavy occlusion image, perspective distortion, and scale variation. And the goal in this research is to solve these problems using a combination of multi-scale aware models and dual path decoder, where you predict both density maps and attention maps for highlighting crowd regions in the input image. In data preprocessing, we cannot use only the crowd count or people count to be the labels for the network because the crowd distribution will be neglected. To deal with the problem, we convolve the height annotation with Gaussian kernel G, which has fixed standard deviation. Assuming that there is a height annotation pixel xi represented using delta function, the construction of density map can be formulated as this equation, and then we will be later calculate the attention map for highlighting the crowd regions by thresholding on the generated density map. There are two proposed models. First one is called M-SFANet because the modifications are done on SFANet. We use unit-like structure with VGG16 as the backbone encoder to learn high-level semantic information, and then additionally insert two multi-scale aware models, namely atrous spatial pyramid pooling ASPP and context aware model CAN. At two different levels of learned semantic information so that our model can understand visual concepts at least from here to here at multiple sizes. Furthermore, we add more residual connections in order to ensure that the learned multi-scale features of the high-level semantic information will impact how the model regress for the final density map. And at the core of ASPP model, the model apply several atrous convolution with different dilated weights in order to learn multi-scale features everywhere in the input image. At the core of CAN, unlike ASPP CAN treats the importance of the extracted scale features adaptively across spatial locations. Hence, the model is proper for dense scenes. The importance of the extracted scale features varies according to the difference from their neighbors. The second proposed method is called M-SegNet. M-SegNet shares almost the same components as in M-SFANet, except for the fact that there are no CAN, SPP, and residual connections to emphasize multi-scale information. And the bilinear upsampling is replaced with max unpooling, so that our MSegNet will have less computational resources than MSFANet with competitive performance and more suitable for speed-constrained applications. And here are some selected results from the paper. We outperformed previous methods in terms of MAE in Shanghai Tech and UCF CC50 dataset. You can see from the left-hand side figure that our proposed methods are able to retrieve the density maps very close to the ground truth. In the ablation study, MSFANet without CAN attains a higher MAE than MSFANet without ASPP on Shanghai Tech Part A, while the results are converts on Sing High-Tech Part B. To summarize, for MSFANet, we add the multi-scale aware models for better tackling drastic scale changes in the input image. And we also add more residual connections. For MSegNet, we change the upsampling algorithm from bilinear to max unpooling. This yields the cheaper computation model while providing competitive counting performance applicable for real-world applications. Thank you for your attention.